Hi, welcome to my presentation. My name is James Broadhead. I'm a current PhD student at TU Delft as part of the ENLIGHTEM project. Today I'm going to be talking about my position paper, which is why intermittent computing could unlock low-power visible light communication. I think the real raison d'etre of the project is to provide a framework for future research by understanding the synergies between intermittent computing and visible light communication, and understanding how we can port over some of the techniques of transient computing, such as checkpointing, to the idea of ultra-low power visible light communication, and understanding how that then enhances performance and provides new opportunities and new sensor networks that we can develop. So our story starts, not dissimilar to a lot in the field of intermittent computing, with the adage that batteries are bad, or that is that batteries have properties that we find quite incongruent with the systems that we want to develop. Batteries are very bulky and restrict the device sizes that we can create. They have significant consequences in terms of our ability to replace them, and also environmentally when we consider our ability to recycle batteries. So this has led on naturally to the idea of battery-free VLC, which we actually find from literature that it's quite topical that there have been a number of recent papers that have looked to develop battery-free VLC platforms. These tend to rely on the fact of energy harvesting and then use either active or more passive forms of VLC to be able to effectively communicate. I think beyond an academic interest in battery-free VLC, there's also a huge push from the real world, and there are a number of applications within the IoT where battery-free VLC would be useful. We can imagine them being used and deployed in smart buildings to collect information about lighting usage or heating, ventilation and cooling. This information could then be used by building managers to provide targeted feedback to reduce energy consumption. We can imagine their use in agriculture and how we could use these devices to collect information about soil pH and a number of other soil factors that may affect the performance of the crop, or within space research, how they can be deployed in very small satellites to collect information and effectively communicate without the need of batteries. So I think there we have quite a strong motivation as to why battery-free VLC is useful. We've seen the number of applications within the IoT where these can be deployed, and we've already seen that the systems community has taken an interest in these devices and already started to develop them. But there are still issues that remain. These devices are on the very constraints of energy and size, and any battery-free architecture is inherently temperamental, it's inherently volatile. These systems will fail because they don't have sufficient energy. So how can we start to reduce the impact of those failures on the network, and how can we improve their overall performance? So the premise of this paper then is to introduce intermittent computing to the field of VLC. Intermittent computing or transient computing techniques have been developed to improve the throughput in failing devices that are battery free. If we take the example of an energy-aware checkpointing scheme, the processing will occur in a volatile memory as usual. However, when there is insufficient energy, this information will be strategically saved to a non-volatile state, and it can then be restored to the volatile state, and processing can continue as normal when sufficient energy is then subsequently available. So these are very simple schemes, but have a very profound impact on our ability to improve throughput and the energy efficiency of these devices, as we have seen from literature. So we think that by porting these techniques over to low-power visible light communication and these battery-free devices, we can gain some of the benefits from intermittency and start to see improvements in performance. So what we've effectively done is develop the idea of intermittently operating visible light communication. On a hardware level, the device that we propose will look very similar to the devices that have already been developed in literature. We think that the device will perform some form of energy harvesting from its environment. It will perform sensing as well to collect data from the world around it. This data may be processed and filtered by the device and then subsequently transmitted through active or passive forms of visible light communication. In terms of the operation of the device, this is an example of an energy-aware checkpointing scheme. So at an upper threshold, the system will then turn on and start processing and sensing and transmitting information from the device. When a lower threshold is reached, checkpointing will be initiated, and the device will save information from the volatile memory to the non-volatile state and go into a phase of hibernation. When sufficient energy is then available, when it reaches the upper threshold, the system will restore from its previous position and continue with the processing and transmission of the relevant information. This improves the performance of the device and can increase the efficiency and throughput of our devices. So we propose that these checkpointing schemes, these operation schemes, should be embedded onto the hardware that is currently available to improve the performance of the devices. So really then, what are the challenges and the research opportunities presented by these devices? I think one of the major challenges is a challenge that's faced by a lot of the intermittent field, the idea that these devices have unknown periods of off time. As we saw in some of the previous slides, these devices will go into a phase of hibernation when insufficient energy is available to them. If we have then two devices that are trying to communicate, if one of these devices is hibernating, it's effectively dead to the network, we're going to have quite significant problems in being able to retrieve the data that has been collected. We also know that if we're using LEDs to transmit, that LEDs to LED needs effective synchronization. And synchronizing under significant power failure or frequent power failure is a huge area of research that has yet to be explored effectively. What then do we need to do? Well, future research should look to two things. It should look to create physical and MAC layer protocols without the need for synchronization. Can we still transmit this information without high levels of synchronization between the devices? Or can we develop synchronization? So it's either that we have to work around the fact that we can't synchronize these devices, or we look to a way to synchronize the devices. Further to the idea of device-to-device communication, we're also going to have quite significant challenges in terms of our ability to scale this up to a network level. Being able to transfer sensor data through a low-powered and frequently failing system is an open problem in research. This is compounded by the fact that devices are likely to be in very similar environmental conditions to neighboring devices, and therefore there may be entire regions of the network that fail because of a lack of sufficient energy. I think the real research opportunity here is to provide more theoretical understanding as to how we can optimize networks to deal with the challenges presented by intermittent operation of these low-powered devices, and also with some of the issues in visible light communication. Another challenge that we're going to have to face in future research is the idea of communicating with non-VLC devices using our intermittent budget. We've developed an intermittently operating VLC device, but a number of other devices on our network may not have the same standards. We can imagine that if we have a number of sensors deployed within an environment, these may transfer information to a central monitor where the information can be processed and useful abstractions can be taken. Cross-technological communication, or CTC, is the idea that we might have to communicate this data to a different set of standards and protocols. What we need to then in future research is to understand how we can either develop new CTCs and how we can use current standardization and the work that's been put into standardizing VLC to develop these CTCs to Wi-Fi and Bluetooth and various other standard protocols. Or we can look at how we can develop and modify current CTCs to perform the same tasks. So besides the theoretical research opportunities presented, what's next for the systems community? I think the implementation for the systems community is actually remarkably clear, albeit the actual implementation is going to be much more difficult. What we essentially need to do is overlay the current transient operating schemes developed in the field of intermittent computing with the battery-free hardware that's been developed in the field of low-power visible light communication. This will then provide the perfect bellwether test to the success of improving energy efficiency and throughput of these devices using these new techniques. What we essentially need to do is build it and they will come. So thank you very much for your attention, and I would love to answer any questions.